UV visible spectroscopy. In the last class I have discussed about the basics of UV visible spectroscopy, that is about the electromagnetic spectrum in detail. So let me brief out today what we have studied in the last class so that you will be understanding in a better way. So what is spectrum? That is, spectrum is a conceptual tool. It is being used to organize and map a set of physical phenomena. So it is composed of both electric and magnetic fields, and these fields are perpendicular to each other and both are perpendicular to the way of propagation of light. And when you consider only the visible radiation for the analysis of visible spectroscopy, so when it will be that is when the white light is made to pass through the prism, it will be split into a different individual colors. These different individual colors indicates the different wavelength energies. That means different wavelength energy is nothing but different energy radiation, different part of the energy radiation in the visible spectrum itself. Okay, so this will be seen as a different colored spectrum. So this, depending upon the type of molecule which we are going to study, we can choose the required wavelength for the analysis of a compound. So all these basics I have already explained to you people. So let me see the remaining part also, that is the one which we have discussed about spectroscopy. That is, it is the study of interaction of matter with the electromagnetic radiation. So as I told in the last class that the radiation, that is any part of the electromagnetic radiation, can be used for the analysis of different types of matter. So that depends upon the type of matter which we are analyzing, and that is the different matters will absorb the different extent of energy. Accordingly, we need to choose the part of the electromagnetic radiation so that the interaction will happen. So when it is interacting with the electromagnetic part of the electromagnetic radiation, then any one parameter we are going to analyze. Either we will be analyzing the absorption, or we are analyzing the transmitted radiation, or we are analyzing the reflected radiation or emitted radiation, and so on. So that is, when we are making the part of the electromagnetic radiation to interact with the matter to be analyzed, and when it is interacting, any one parameter among this we will be using for the measurement of concentration of, or you can say both for qualitatively and quantitatively we can analyze the matter. Electromagnetic radiation also we have studied in the last class. That is, what is electromagnetic radiation and what are its properties. Just I will brief out once again. So electromagnetic radiation is a radiation which is composed of both the electric and magnetic components. These electric and magnetic components will be perpendicular to each other, and both are perpendicular to the way of propagation of light. And we have studied about the wave nature of the electromagnetic radiation and particle nature of the electromagnetic radiation, and some terminologies like what is frequency, wavelength, wave number. So all these things we have studied in the last class. And also the subdivision of the other neighboring wavelength that is regions, like with reference to the UV visible, the IR and UV will be subdivided into near UV and far UV, that is with reference to the visible radiation. By keeping visible radiation as a reference, so the radiation which is near to UV, it is called as near UV, and the radiation which is far from the visible, it is called as the radiation which is UV radiation which is near to visible radiation, it is called as near UV, and the radiation which is away from the visible radiation is called as far UV. And in the same way, even IR also is being subdivided into three parts, that is the radiation which is near to UV is being categorized as near IR, and the radiation which is far from the visible which is being categorized as far IR. So with reference to the visible radiation, these two will be subdivided into near and far, whereas in case of IR it will be subdivided into three parts, not only near and far and also mid IR. So this mid IR region we will be using normally in the laboratory for the analysis of compounds to identify the functional groups which are present. Normally the mid IR region we are using. So all this we have discussed in the last class, and also these terms also we have discussed in the last class. You need to remember all these things before we start the chapter, and also the different regions of electromagnetic radiation, and which we will be studying in detail here are UV, visible and IR. So at least for these values you need to remember. What is the far UV region and what is the near UV region? Visible region is where, and near IR means from where to where, and mid IR means where to where, far IR means where to where. So you need to remember all this. And also to remember in the easy way, I have given here all the wavelength of radiations in terms of nanometer. Normally the wavelength, as the wavelength increases, the unit for the wavelength will be changed to per centimeter. Just to remember, and it will be convenient for you, so that I have given the values here. But when we are doing the measurement, the far IR and mid IR, all these things near IR, we will be measuring in terms of per centimeter. Why? Because when we are measuring in terms of nanometer, it becomes a huge number. This I already explained why it is and how it is. Just say for example, when you are measuring a small distance in terms of micrometer, if the distance is little bit longer, say for example, if you want to measure the length of the book, so you cannot measure in terms of micrometer, so you need to go for measuring in terms of centimeter. But if you want to measure the distance from our college to Hegde Nagar, you cannot measure the distance in terms of centimeter or meter. So, but that has to be measured in terms of kilometers. But when you want to measure the length of the classroom, so you have to measure in terms of not even centimeter, not even meter, you have to, not even centimeter, not even kilometer, so you have to measure in terms of meter. So in the same way here, when we want to measure a longer distance, and we cannot use nanometer. If you take a nanometer, the values becomes very huge numbers. Only because of that reason, it will be for our convenience, we will be measuring in terms of per centimeter. But anyway, the value will not change. But to remember and to make it easier, so we can measure in terms of per centimeter. So this and all I have discussed in the last class. Let us see now what all these terminologies also already have discussed in the last class. Please do remember all these terminologies. And this also, why do the compounds will absorb at different energies, I explained in detail. That is, as we know that the energy of the photon is exactly the same as the difference in the energy between the ground state and the excited state of an atom. So different atoms will have the different extent of this energy. And this energy, how much is the difference in the ground state to excited state, whatever the energy difference is there, no, that much energy will be absorbed by the supplied the radiation. That much energy will be absorbed by the supplied radiation. So that is why different atoms will have this different extent of difference in the energies. So when one atom is having energy difference between ground state to excited state will be different than that of the other different compound atom. So as a result of that, we could able to differentiate the different compounds, and this will be helpful in analyzing the compounds because of only this reason. And the other terminologies also already we have studied. Let us see now the UV visible spectroscopy and the other different spectroscopic parts which we are going to study are IR, UV, IR, NMR, UV and visible. So that we will discuss later in the next chapters. Let me go through the last class discussion, that is about the different electronic transitions. So different electronic transitions we have studied in the last class, that is the possible four types of transitions are sigma to antibonding sigma transitions. That means when the electron which is present in the sigma bond will absorb the radiation and it goes to the higher excited state, that is it goes to the empty orbital, that is called as anti-bonding orbital. Sigma star is nothing but anti-bonding orbital. When the electron which is present in the sigma bond will gain the energy and it gets energized, as a result of that it will jump to the higher energy level, higher energy state. So it is called as anti-bonding sigma. So this anti-bonding sigma is nothing but it is in higher energy empty orbital. Whenever the electron is energized, so it will be placed into the higher energy orbital and it is called as anti-bonding orbital. So in the same way, non-bonding to anti-bonding transition is possible, non-bonding to anti-bonding pi transition is possible, and pi to anti-bonding pi transitions are possible, and you have studied in the last class in detail about all these types of transitions. That is, the compounds which are containing non-bonding electrons will undergo non-bonding to anti-bonding sigma or non-bonding to anti-bonding pi transitions depending upon the extent of energy it absorbs, and pi to anti-bonding pi transitions, and we have studied already in detail in the last class with the diagram also. That is, when it is been asked in the examination, you need to write with the diagram. Normally it will be asked for 5 marks, so you need to write with the diagram, so your answer will be more accurate. And as soon as just by seeing the diagram itself, we can understand that you have understood the concept, and it will be easier for you also to write and explain. So better you have to write the diagram and explain during the examination. So you can see here occupied orbitals, that is these are the orbitals which are in the ground state, that is sigma, pi, non-bonding, whereas pi star, sigma star indicates anti-bonding orbitals. So these are the orbitals which are at the ground state, that is the one which indicates n, pi and sigma. So these are the electrons which are at the ground state. When it gets energy, you can see that when it is getting absorbing the energy, it gets energized and it goes to the higher excited state correspondingly. That depends upon the molecule. So this all we have studied in the last class. And the transitions which are absorbed by UV visible are normally pi to antibonding pi will be the stronger bond we observe, that is absorption band, and non-bonding pi to antibonding pi will be very weak and sometimes it will not be absorbed at all. So pi to antibonding pi transition is absorbing at the lower energy. Why? Because we have already explained to you people that is why it is at the lower energy. That is, as we know that pi bond is a weak bond and the electron which is present in pi bond will be possessing lesser energy. So accordingly it will absorb the lower energy radiation. So it will be getting excited and goes to the higher antibonding, that is excited state. It is called as antibonding pi. So pi to antibonding pi transition will be normally happening at lower energy levels. And non-bonding to pi I'm very sorry. So non-bonding to pi transitions, that is antibonding pi transitions, is happening at a lower energy, whereas pi to antibonding pi transition will be taking place at the higher energy. So here comparatively, when compared to non-bonding to antibonding pi to antibonding pi transition will take place at higher energy. But when compared to sigma to antibonding sigma transition, the pi to antibonding pi transition will be lesser. It will show at the lesser energy. With reference to that I explained. So you can just remember comparatively, that is when you compare non-bonding to antibonding pi transition and pi to antibonding pi transitions, so you need to remember the differences between the different types of transitions here. That is non-bonding to antibonding transition happens at lower energy, and pi to antibonding pi transitions is taking place at higher energy. When you compare these two types of transitions, pi to antibonding pi transition is at higher energy, but when you compare pi to antibonding pi transition with sigma to antibonding sigma transition, sigma to antibonding sigma transition happens at higher energy, highest energy, whereas pi to antibonding pi transition takes place at lesser energy when compared to sigma to antibonding sigma. So that is what I told in the initially. But when we compare non-bonding to antibonding pi transition and pi to antibonding pi transition, so the thing is comparatively when it is these two are compared, pi to antibonding pi transition is happening at higher energy, whereas non-bonding to antibonding pi transition is taking place at lower energy. So these are the examples which we have studied already in the last class. So you please remember all these with examples, and with the structure and examples with values you need to remember, which we have discussed in the last class. So now let us see some terminologies which are used here, and that is the definitions and examples of these. So this is the basic concept actually involved in the UV visible radiation. So any molecule to undergo absorption by using either by using UV or visible, it must contain a chromophore. So chromophore must be present in the molecule, then only that molecule will absorb either UV or visible radiation. You please remember this. To absorb either UV or visible radiation, a molecule must have to have a chromophore. Then what do you mean by chromophore? What is a chromophore? That is, the chromophore is nothing but it is an unsaturated moiety which will absorb the radiation. It is an unsaturated moiety, a part of the molecule which is unsaturated, and it will absorb the radiation, is called as a chromophore. So or you can say that the group or the atom which is present in a molecule will absorb the radiation. Either it may be an unsaturated moiety or it may be a particular group which will show the absorption in the visible or UV region, that is called as a chromophore. So these are the examples. You can say that Br, bromine, OH, and imine group. NH2 is amine, NH, that is C double bond NH, is imine group. So these are all the examples for a chromophore, that is carbon-carbon double bond and carbonyl functional group, and so nitrogen-nitrogen double bond, carbon-carbon double bond. All these are the examples of chromophore. So you can note down some more examples of chromophore, that is